Hi guys, so this video is going to be the second part of that unit. So we've seen the variation of ionization energy across a period. Now we're going to see it down a group. So we have three elements here that are from group 1. So let's see the electronic configuration and the number of inner shells. So these are the electronic configurations, and so the number of inner shells, so lithium. So if this is the outermost shell, so that would be the inner shell. So there's one inner shell. So that's the outermost shell here. So we have 1, 2 inner shells. And if this is the outermost shell, so we have 1, 2, and 3 inner shells. Okay, so as the number of inner shells increase, so what's going to happen to the shielding effect? So remember in the previous video, we talked about the shielding effect. So if this is the nucleus, the more shells you have between the nucleus and the outermost electron, so more shells you have, the inner shells are going to act as a shield. They're going to screen the force of attraction of the nucleus to the electron. So the more you have shells in between, the more is the shielding effect, and a higher shielding effect means that ionization energy is going to be lower. So inner shells increase, which means that ionization energy is going to decrease down a group. So it becomes easier to ionize elements down the group, because if you look at the number of shells, so down the group, elements become bigger, right? The atom becomes bigger, so there is a greater distance between the nucleus and the outermost electron. And there is also a greater number of shells between the nucleus and the outermost electron. So there's greater shielding effect. Okay, so of course, there's also the nuclear charge that increases down the group. Normally, if nuclear charge increases, the attraction between the nucleus and the outermost shell should increase. But in this case, it's the shielding effect that predominates. So shielding effect predominates over nuclear charge. So outermost electron becomes further from the nucleus and less strongly attracted. So if we look at this graph, so this is what we see. So this is across, all these are in the same period. So across a period, you see the trend, the increase in ionization energy. And if we look at the elements down the group, so let's say, so this is lithium, sodium, potassium. So you see there is a general decrease in ionization energy down the group. Let's look at another group. So that's group 2. So you see there is a general decrease of ionization energy as we move down the group, and there is a general increase in ionization energy across the same period. So you see, so that's the first period, that's the second period. So a lower period, the second period, the ionization energies is going to be less than the first period. Okay, so that's because of an increasing shielding effect which predominates over the effect of the nuclear charge. So this diagram shows the increase in size of the elements down the group. So increase in size, and this means increasing shielding effect. Now, the fact that we are able to remove electrons from an element one by one, So we have first ionization energy, second ionization energy, third ionization energy. So in case of aluminium, we'll have till the 13th ionization energy. So we are able to remove electrons one by one, and this ability has given us the evidence that electrons indeed exist in energy levels. So the data obtained provides evidence for existence of energy levels. So if you write the electronic configuration of aluminium, so when we are going to be removing electrons, we'll remove electron one by one. So this one will go first, then second one, third one, and we're going to go on so forth. And if we measure the ionization energy, so you'll see first electron removed out, so that's from the free P1 that is removed. Then you have from the free S, which is removed, and from the free S again, which is removed. Then the fourth electron is taken from an inner shell. So that's the inner shell here. So that's from the 2p. So the 6 electrons that's going to be removed from the 2p. So 1, 2, 3, 4, 5, 6. And then these are going to be from the 2s. Okay, so which means that all these electrons are removed from the second energy level. And then these two, the last two, are going to be removed from the first energy level. So there's the 1s and the 1s electron. So this gap, this big gap in energy here and big gap in energy here shows that electron is now being pulled out from an inner energy level. So as soon as you see a gap, it's telling you that we're moving to an inner energy level. So the first three are relatively easy to remove as they are in the outermost shell. There will be a sharp increase when the third and the fourth electrons are being removed. So here there is going to be a slight increase, but here you see the sharp increase. That sharp increase is because the fourth electron is removed from an inner shell closer to the nucleus and requires more energy. And there is again a large difference in ionization when the 11th and 12th electrons are removed. So over here you have a second large gap. Now the electrons are removed in reverse order of the electronic configuration. So number of electrons in the first section of the graph is equal to the group number. So if this is the graph of ionization energy against number of electrons removed, so this is the first portion of the graph. This is the second portion. So the first portion is just before that big gap occurs. So this is the big gap that is occurring. And so this is what is indicating that we're moving to an inner shell. So whatever is in the first portion of the gap indicates that electrons are removed from the outermost shell, outermost level. And this is going to give you the group number. So here we can count 1, 2, 3, 4, 5. So this is from group 5. Okay. And if you look at this one, the gap occurs here. So this is from group 1. So I'll do this one for you. Sketch the graph for the elements. So carbon 6. So carbon, there's 6 electrons. So 1s2, 2s2, 2p4. So 2p2. So which means that the outermost electron removed are these ones. So we'll start with this one first. Then the second is going to be from the 2p itself. The third and the fourth will be from the 2s. And then the last two is going to be from the 1s. So first electron removed here, second, third, and fourth. After that, we are moving to an inner shell which is going to be these two. So then we'll have a gap and then these two. So 5 and 6. It's just a sketch, so there is no values over here. So you see this gap occurring at the point where the electrons are being removed from an inner shell. F, fluorine. So there is 9 electrons. So fluorine, you already know fluorine is in group 7. So the first 7 electrons are going to be from the outermost shell. So they will have lower ionization energy. So I can have it like that. Okay. And so these are the 7 first electrons removed. And then the last 2 are going to be removed from an inner shell. So we need to show the gap. So these are the last 2. And you can draw the individual dots for the 7 electrons. Identify the group number of the following elements. I'll do this one. I'll do one for it and then you complete the others. So how do you find the group numbers from the ionization energies? You have to look for the gap. The one which shows the biggest gap, like a very huge gap between the first, between the initial and the second value, means that there has been electrons removed from an inner shell. So if you look at the values here, 700, 1400, so we're around adding 700. And here you see that we're adding actually around 5,000 to this. So there is a big gap here. So for X, already the gap you can see 1 and 2 here. So which means that this has been a group 2 element. So when you're seeing the gap, means that electrons are being removed from an inner shell. Here we're adding around 3,000, around 3,000, around 4,000. So all of these you're adding approximately equally. So there is no huge gap. So try to find the group of Y and Z.